first graph has a parabola shape, which means
Quadratic.
and the second one, it's a linear. So not quadratic. If you look at this example right here, your highest exponent is 2,
That's quadratic.
so that's a quadratic equation. Second one, highest degree is 1. And move on. Often formula representing real-world situation contain 3 variables: the dependent variable and 2 independent variables. For example, in the formula of the volume of a cylinder, you have the volume equals pi r squared times h. What would be your dependent variable?
H. No, R.
There's one more. V. V depends on both r and h. Okay? So V is your dependent variable, while your 2 independent variables are r and h. So V is the volume, r is your radius, and h is your height. So in reality, we can't have 3 unknown variables. Okay? We always should have 2, right? Because then I can relate them. I can relate them in a table of value, I can graph them. So I have to set one of them to be constant. Okay? So to determine the relationship between the dependent variable and one of the independent variables, set the other independent variable to some constant value. Okay? So in this case, you're going to set either the radius to a constant value and say, I want to make my cylinder this radius. I can change the height. Or you can say, I want to set my height, so I want the height to be this much, and I can change my radius. Okay? So you have to set one of them to a constant. You rearrange the equation to solve for the variable, to solve for the dependent variable. And you're going to determine if the equation is linear, quadratic, or some other nonlinear relation. So let's look at the example. So the formula d equals 1/2 at squared gives the distance between traveled by a car as it accelerates from a stop position where d is the distance traveled in meters, a is the acceleration in meter per second squared, and t is the time elapsed in seconds. Investigate the relationship between d and a when t is 2 seconds. So let's go back here and tell me what are your 3 variables.
D is the distance.
D is a distance, so D is a variable.
A is the acceleration.
A, acceleration.
And T is time.
T is time. Which one is your dependent?
D.
D is your dependent, and it's depending on what?
And
And.
Acceleration.
Now you see that this question, part A, it's setting t to 2 seconds. So it's giving a set value for t. So now I only have 2 variables. If I set t to 2, now you only see 2 letters, d and a, right? So d is equal to 1/2 a times 4, right? I can simplify this. What's 4 times 1/2? 2. So the equation look like this now. D equals 2a. Much simpler, right? So now this is the relationship between D and A. Do you guys agree with me? So the relationship is D equals twice A. What kind of relation is this? Quadratic or linear?
Linear.
Linear. Yes.
The question was backwards. If it was going from a start position to a stop position, would it be different or would it still be linear?
What do you mean?
Because like it says the car starts, it accelerates from a stop position. If it was already driving and then it stopped, would it be different?
It would also be linear, but will be negative.
What do you think?
Will be negative 2a. Because it's decelerating, that means your acceleration is going down, which means it's a negative acceleration. Okay. The second part is asking you to investigate the relationship between D and T when A is 2. So now I still have the original equation. But now the set constant is what variable?
T and D. Constant is A we have, but different.
A is constant, and I'm looking between D and T. So I'm gonna sub in 2 for A. So that equals to D equals T squared. So that relationship is
Quadratic, yeah. It's a parabola.
Are you guys okay with this?
Well, what do you do with between the 1/2?
Sorry?
What do you do with between the 1/2?
2 times a half is 1. Right, but we don't write 1. So, again, I'm given 3 variables, then they give me a set constant for one of the variables, then I end up with 2 variables. It's too many variables in one sentence. Okay. You done copying this? So right now we're gonna have to use the Excel again. So quadratic model to that. So we can use quadratic regression to model data that appear to lie along a parabolic curve and produce a curve of best fit. So this is something that you have to try. You have to test it on Excel. So if you see that your points are going like this, right? Obviously, you're not gonna try your linear regression, right? It's kind of obvious that it's a quadratic regression, okay? So you see how when we did the Excel sheet, there was a list of different regressions and the second one was linear and we picked the linear one. So in this case, we're gonna pick the quadratic, okay? So I want you to try to put these in Excel and try to graph them, do like a scatter plot, and find a regression line. So same what we did, but the only difference this time is we are picking a quadratic regression line, okay? This is gonna be on your X, so you're gonna put this on the first column. This is gonna be your Y, so you're gonna put this on your second column.